Good afternoon, ladies and gentlemen. It is my pleasure to come here again to Caggio from the Institute of Mathematics of the Academy of Sciences. Matteo Caggio has many analytical contributions concerning fluid flow problems, but also structural problems. And today he will talk on Mach number regimes for capillary fluids. So please take the floor.
Thank you for a nice introduction. Good afternoon. So today I would like to present to you a sort of summary and also work in progress of some result of few years ago, also recent result, and the result that we are still working in progress with potential also future interest. So this is a joint work with Matteo from Italy, from L'Aquila, and Lars Erik Pinch, I don't know if the pronounce is correct, that was postdoc in the same city, and then he moved back to KIT in Germany. So the talk will let's say go around some singular behavior of the Mach number for a class of fluids that we call capillary fluids, so fluid with capillarity. So in general, the model that we wanted to consider, it's a compressible Navier-Stokes equation for a barotropic fluid, so the temperature is constant, so the pressure is a power law of the density. So, and you can imagine that, let's say, these fluids, this kind of model is representative of the fact that inside your fluid there is a sort of phase boundary. So if you imagine that you have a phase boundary when you have a completely different density between one part and another part of the fluid or another kind of material, there is a contribution of energy of the fluid given typically by the gradient of the density. So there is a quite huge theory behind it, developed already in the beginning by van der Waals, Korteweg, and other people. So you can find a nice reference in this book, Molecular Theory of Capillarity. And this contribution of the energy results in a change in the stress tensor with this general law. So this is the law that was this kind of tensor was derived by Korteweg based on previous theory of van der Waals. If I remember properly, Korteweg was a student of van der Waals. So he derived, with respect to this phase boundary flow, this kind of tensor. So you can, let's say, in literature, find a different kind of fluid related to the behavior of the capillarity coefficient kappa. So in our case, we are considering probably one of the simpler examples. So we have a constant k. This square is just a question of physical dimension. So our tensor will look with this capillarity coefficient constant. So typically in literature, and it's called capillary fluid. So fluid that where you can see some capillarity effect. So one more thing, our viscous, classical viscous term is density dependent viscosity. There is a reason why in this kind of analysis we need a fluid of this kind. So our interest is in discussing a density-dependent fluid with this kind of behavior of the Korteweg term, and to study some problem related to this. In this kind of framework, there is a French school in the last 20-25 years that developed several works, several analyses around viscosity-dependent fluid, density-dependent viscosity fluid, and in general, the relationship that is connected the two viscosity coefficient is the common and famous Bresch-Desjardins entropy inequality, in which the viscosity coefficient, in order to preserve a particular type of kinetic energy inequality, they have to obey this kind of algebraic law. There is nothing physical behind it. This is a, let's say, an artificial relationship that gave us the possibility to preserve a type of inequality concerning the kinetic energy that we need for the analysis for compactness argument, stability result, resistance result of this kind of equation. So One simple case is to have a linear dependence of this viscosity coefficient, so the shear one, and consequently, respect to this relationship, you have the bulk viscosity equals 0. So this is basically a simple setting. Potentially, you can develop also the same analysis for more general coefficient, namely nonlinear, but as a first step, we are in this kind of setting. So which kind of interest we have around this model, and why we choose also a model where there is a presence of this term? So, inspired by previous work, where this kind of tensor was not present, so I am referring to the work of Arspot and Liang, we were interested to see which kind of property of this model we have in the high Mach number limit. So you can imagine that you rescale physically your model respect to some fluid dynamics parameter, and in front of the pressure you have the Mach number. So if the Mach number is going to infinity, formally speaking, you are losing the pressure. And this is one of the, and this is one part of the analysis that we are interested in. And if the Mach number is going to 0, there is a gradient of the pressure that basically dominates, let me say it this way, on the other terms. So consequently, the gradient of pressure is 0, the pressure is constant, the density is constant, and you drop in the incompressible flow. So we wanted to study this two regime, what happened in the high Mach number limit and in the low Mach number limit, and to see which kind of property also we have respect to this. So why this tensor, and why also the density-dependent viscosity? So why the choice? The previous work, that as far as I know, there are the only two previous workers before our result on the high Mach number flow, concern the fact that they didn't have the quarter tensor, but they didn't have also the existence of the solution for the fluid without pressure. So they just study stability analysis, so assuming that the solution of the pressure system existed. In our case, we study also the existence of weak solution in the case the fluid is completely pressureless, and we also prove the convergence. So we did one more step forward, but we needed this tensor in order to have a reasonable control on the density in order to prove the existence of weak solution for the pressureless system. So without this term, as far as I know, the problem is open, apart in some particular case that I will describe you later. Moreover, we wanted to study also the opposite, so to insert ourselves in a weak strong uniqueness framework. I will tell you more later what I mean about this. And also to study a low Mach number flow, so the opposite limit, and to study also some property connected with the heat equation in the pressureless limit. So this was basically the framework that from a few years ago, 2021 up to now, we are studying. There is something already proved, something that is recently proved, and something that is in progress. So concerning the existence of weak solution of this system, so the story started almost 20 years ago by the French school, Bresch, Desjardins, and Lee. So where they studied the existence of this solution for the Cortez system with a particular choice of test function. This was somehow a technical trick in order to handle the compactness of the convective term. So they introduced some function density dependent. They have a lot of control on the density in the regularity norm, so they were able to study the existence, to prove the existence of weak solution under this particular choice of the test function. Again, this choice helped them to handle the convective term, because in principle, this control doesn't imply compactness of this term when you want to pass to the limit in the weak formulation. More recently, indeed in L'Aquila, Antonelli Spirito, they prove the existence of weak solution in the three-dimensional torus for this system but with the, let's say, usual weak formulation. So the vacuum regions are allowed in the weak formulation, and their argument are some truncation argument and other kind of things that they give to them the possibility to prove the existence of weak solution. So somehow we base ourselves on this kind of framework in the and also in this one in the second step. So with the Donatella we prove the existence of a weak solution of the pressure for the pressureless system in the framework of Brescia. And this could be indeed extended also in the framework of Antonello Spirito. So the first step was to prove with this choice of the test function, motivated by the fact that you have a lot of control in the regularity of the density, but also you can prove the same in this kind of framework. And also we prove the weak convergence for epsilon to 0. So I wanted to stress again the fact that without the quarter tensor, I don't know any result about the pressureless system, if not just stability result, when the Mach number goes to infinity. So one thing that we did with Donatella is, okay, the Cortex system is giving to me a possibility to have a little bit more control on the density. So I have both the possibility to prove the existence of weak solution and also to pass to the limit with the Mach number that is going to infinity. Moreover, the fact that we have the density-dependent viscosity is giving also information on the density that is giving to us the possibility to pass to this limit with or without the quarter tensor. Namely, if you have a fixed viscosity coefficient, constant, and you don't have any dependence on the density, up to now, I don't know any result about the pressureless limit, because you lose the control, the integrability rho to the power gamma of the density, and you are not able to recover from, as far as I know, from any other terms, anything about the density. So the problem is open for constant viscosity coefficient. For coefficient that they are density dependent without the quarter tensor, there is a stability result or a singular limit result in the limit of the high Mach number, but there is no existence of the pressureless system. So this was basically the state of art behind this problem. So with Donatello, we were able both to prove the pressureless system, the existence for weak solution of pressureless system, and also to prove the weak convergence for epsilon to 0. So I mentioned before that there is a link with the heat equation of the pressureless system. So one result that is connected to our previous analysis is the following. So if you consider just an initial density L1, strictly positive, and you assume that your initial velocity is basically rotational, so you introduce an arbitrary potential, and the gradient of this potential is your velocity, or in the initial state, you are able to prove that there exists indeed a smooth solution of the pressureless system, such that the density solve the heat equation. And this, it works just for the pressureless system. So this is also the condition in which Hasport and Young, they were able to prove a smooth solution for the pressureless system also without the quarter tensor. So we basically readapt the result to the quarter tensor. But as far as I know, the only existence of, in this case, a smooth solution for the pressureless system, you have it under this condition that can be also relaxed to weak, existence of weak solution. So under this condition, you can prove existence of strong and weak solution for the pressureless system also without the presence of the quarter tensor. But just under this condition, in general, the problem again is open. So this was another result that we studied with Donatella. And more recently, we were interested to what is called usually the weak-strong unique problem. So that the weak solution coincides with the strong solution in the moment that the initial data for both the solution are the same. This was a problem not studied in this kind of framework. So, and we studied it through some relative energy method, and in particular, we were forced to use what is called in literature an augmented version of the Navier-Stokes quarter sensor. So what I mean in this for this. So if you want to prove a weak strong uniqueness result in the context of density-dependent viscosity fluid, you have a problem with the viscous tensor because you are in a condition in which the fact that you have your viscous tensor that is dependent, where the viscosity is dependent by density, means that when you have a weak formulation and you move the divergence of the test function, you lose the H1 norm of the velocity. So you basically don't have any information on the velocity due to this guy here. If you have a constant viscosity, you have it. And this is the problem in the context of the relative energy method framework, because you don't have the possibility to apply any kind of Korn inequality type, for example, in order to close the computation. So this means that the suggestion is typically to create, to augment the system with another velocity. Let me call it the phi rho. So you have an equation for one more velocity, and this phi rho is such that is defined in the following way. So in particular, in our context, this will be a gradient of log rho. And this has a dimension of the velocity indeed, because the kinematic viscosity is a length square over time. And you have here the gradient, so this has a dimension indeed of the velocity. Okay. Here you have just rho, so you don't count about this because you're gradient of rho over rho in our case, so you're gradient of logarithm of rho. So this indeed is a quantity that is a velocity. You augment your original system, you write one more equation for this, and in the relative energy framework, you are able to prove the weak strong uniqueness, both for the pressure system and pressureless system, and in particular, you are able to prove that in the limit of Mach number that is going to infinity, you have that the weak solution of your quarter-X system with the pressure converge to a potential strong solution that you assume that it exists at this level. So you have not just the weak convergence that I mentioned before, but also the weak strong convergence in the relative energy framework. So you can do better than this. So here, in this kind of result, we assume the existence of the smooth solution, the strong solution in the limit, but if you, this is the result of the weak strong uniqueness. So if we have a weak solution of the quarter-X system, and we assume existence of the potential strong solution that start from the same initial data, so indeed we have the weak strong uniqueness property. But you can do better than this, because if you put yourself in the same framework that I mentioned you before, you indeed have the existence, you can prove the existence of your strong solution. So indeed, in the pressureless case, we have both the existence of the weak solution, the existence of the strong solution, and we can prove also the weak strong uniqueness in the pressureless case. So this is what we did up to, in the last years concerning the high Mach number limit. So now the point that we want to do the opposite. And this is partially is a work in progress and partially has some already some results, but we are finishing the paper in that direction. So the idea is now to see what happened in the opposite limit. So if the Mach number goes to 0, again, this term dominates on the other one. So again, you have a gradient of pressure that is 0, pressure constant, density constant. So because you have a density constant, and the quarter-X tensor is just a part of the term of the fluid that is dependent by the density. Indeed, in the low Mach number limit, you end up in the incompressible Euler, for which we know that for suitable initial data in some regularity class, we have the existence of the classical solution. So here I mentioned that I wanted to pass to the limit both with the Mach number, then with the viscosity. The reason is that, as far as I know, in the relative energy framework that I mentioned you before, and I will show you in a few minutes, I'm forced to go also in the vanishing viscosity limit. So I don't know any result in that framework in general for different kind of model where you can avoid this. As far as I know, you are forced also to go to the viscosity to zero. And this creates a bit of problem here indeed, because in your a priori estimate, you have something that can blow up when the viscosity goes to zero. So you have to change the machinery in the viscosity limit with respect to the Wickstrom uniqueness. In other words, the Wickstrom uniqueness has to work with the augmented version of the system. But when you go in the vanishing viscosity limit, you can bypass this and to work just with your original system. And this is, I mean, the reason is that you can play with a proper definition of the viscous stress tensor that I will show you in a moment. So the idea is to do this, and in particular to treat the potential presence of the acoustic wave in the limit. So if you perturb the initial density of your fluid, the basic density of your fluid that you can imagine that is incompressible, you have the potential presence of acoustic wave in the system that is making the problem more interesting. So this is also the part of the analysis that concern the low Mach number limit. So what I mean about the acoustics wave, so you can rephrase your compressible Navier-Stokes system in the acoustic analogy. So if you imagine that your incompressible density is perturbed with respect to the Mach number epsilon, you can write the acoustic system that is related to the compressible Navier-Stokes equation. So you can have extend also the quarter tensor in power of epsilon, and assuming that epsilon indeed is going to zero, you can just remain in the first term. So this is the second term, you can neglect it. So, and you have, when the power of epsilon is just one, I mean, you have the acoustic analogy of your compressible Navier-Stokes quarter system. Typically, in the compressible setting without the quarter tensor, you don't have this term, and so you have the usual acoustic system. So namely, if you multiply this equation by gradient, formally speaking, and this equation by time derivative, and you sum up, you indeed have an acoustics equation in the end. So the difference between the acoustic analogy for the usual compressible system and quarter is exactly the presence of this term, that in the low Mach number limit will give to us a different kind of dispersion of the acoustics in the low Mach number limit setting. So we have to handle basically this system in our relative energy framework. So where is here the difficulty? So we need some suitable dispersive estimate that they will damp our acoustic wave in the limit of the Mach number to zero. And this is quite subtle, because we need to, let's say, symmetrize or anti-symmetrize, because there is plus and minus here, the system in a suitable way. So we rephrase the system with this variable in order to have basically the same operator here. The reason is that usually when you have this system, if you drop this term, somehow you have the divergence of gradient here. So you are able to handle the dispersive analysis, define a proper differential operator in order to have your dispersive estimate. But here you have one more term. So you need to have a sort of symmetry between the two equations. So this is the reason why we rephrase the system in this way in order to have this symmetry before the two operator, for the operator. Then, in our case, it's enough to work with the homogeneous system. These are, for technical reasons, there is nothing too much deep in it. And then the point is that this system can be characterized by this semigroup operator, where this H is of this type, and this H is defined through its Fourier multiplier. And the Fourier multiplier is of this type. And here there is a bit of analogy between the physics behind this dispersive relation, here is in Fourier space, and our model. Indeed, almost, more than 70 years ago, Bogorio derived a dispersion relation for the wave that they are characterized by this system. In particular, in that work was done for a Bose-Einstein condensate, so a quantum wave, let's say. So through the manipulation, the Gross-Peter-Higgs equation, that is a nonlinear Schrödinger equation with some wave property. So in order to have this relationship, one, let's say, algebraic computation could be looking for a plane wave solution of a linearization of this equation, and then by some algebraic manipulation, you are able to derive the fact that your indeed dispersive wave has this kind of dispersive relationship. This dispersive relationship is connected to the usual dispersive relationship for the linear acoustics, that if you drop K here, you have exactly the dispersion of the usual acoustic wave, that is the modulus of this frequency. So this is something that indeed it's a little bit more deep than this. So let's say that in the physics of the Bose-Einstein condensate, this discussion is just to have a parallel between our model and what is known in the physical literature. In the physics of the Bose-Einstein condensate, so Bogoliubov was able to create to derive in 1947 an approximation where you are able to diagonalize your Hamiltonian and to derive one part that belongs to the basic state of energy and one part that is connected to the energy level of your Bose-Einstein condensate through some operator that are called usually ladder operator or creation and annihilation operator. I think introduced the first time by Dirac. And then you derive indeed the dispersion relationship that is the same that we have in the frequency space, has the same flavor. So this kind of dispersion relationship is telling to you that for small momentum, indeed your system behaves like a usual acoustic equation that you can derive from the compressible Navier-Stokes system. And is a free particle nature in the sense of Schrödinger for large momentum. And it was a big work to prove mathematically that this relationship in physics is indeed, is a reasonable, is correct relationship. And this was, you can check the paper of Boccato, Brennecke, Cenatiempo, and Schlein. Also, Serena Cenatiempo is in L'Aquila. So, and they really prove that mathematically, not just from physical argument, that this relationship indeed is inside the model, the nature of the model. So this just to give you somehow the idea that there is basically a link between the dispersive relationship that we are using in the Mach number limit and the physics we have. So, and this is what you can indeed derive from our system. So, considering an admissible coefficient called Schrödinger admissible coefficient, you have this dispersive estimate respected to the Mach number limit. So in your evolution of a state is indeed bounded by the state at time, let's say 0, respect to the Mach number. So maybe it's a bit abstract here, but if you imagine that this quantity is your initial data, and you evolve the initial data by this operator, you are bound by the initial data itself by rescaling with this Mach number. And if you plug this through a Duhamel formula in acoustics, you are able to derive proper dispersive estimate for your acoustic system in this norm. So this means that when, I will arrive to this slide in a moment, when we applied our relative energy framework, in the low Mach number limit, we need this kind of control on our acoustics in order to converge from the weak solution of Navier-Stokes to the strong solution of Euler in the low Mach number limit. In particular, for technical reason, we need a suitable regularization of initial data to have all the regularity that we need for fixed delta. So in principle, there is before the low Mach number limit and then the modified parameter will send to 0, but for technical reason, we need to regularize the initial data from the beginning. So why all this story? Because we wanted to create a framework, as I told you before, a relative energy framework, in which we compare a weak solution of our system with a potential strong solution in the limit. So here, capital U and R are arbitrary smooth function up to this level. And rho U is a solution of our Navier-Stokes system. This part concerned, I didn't write any definition of H, but H is connected to the part of the energy, and it's bigger than 1, okay, in our setting. So this functional is basically giving you a difference between your weak solution and your strong solution, roughly speaking, both in the kinetic energy part, in the pressure Helmholtz free energy part, and in the part that concerns the energy due to the quarter tensor. So this, through a manipulation of the weak formulation, so any weak solution of your Navier-Stokes quarter resistor satisfied indeed this inequality. Okay, you can prove this for arbitrary smooth function U and R. And what you do indeed, so you, as an ansatz, you insert in this smooth function exactly your acoustics that has to go to 0, has to have dispersion in the low Mach number limit. And here I wanted to stress one thing that, as I mentioned before, if you can construct this framework also for the augmented system. So for the weak strong uniqueness, we did this work. So we created this relative energy inequality for this augmented system, and we were able to get the weak strong uniqueness. But if you want to do the same, and you wanted to send the viscosity to 0, you have some trouble in this term, because this term is blowing up when the viscosity is going to 0 due to the fact that this term here is connected to the Brèche-Desjardins energy inequality due to the fact that the fluid is density-dependent viscosity. So it's much more convenient to keep the viscous stress tensor together in your computation. So this is the appropriate definition of the stress tensor due to the fact that you don't have really any information on the velocity. So you have information on the momentum, you have information on the kinetic energy, but the velocity itself is not well defined, for example, in the vacuum. So the correct definition is this one, and through this correct definition, you can build this stuff, and you can have a weak strong uniqueness with this stuff. But when you want to do the vanishing viscosity limit, it's much more convenient to create a framework on which this tensor, indeed, that is in L2 in time, L2 in space, is compact, is not splitted. This belongs to all the computations in this framework. And as an ansatz for a fixed modifier parameter bigger than 0, you insert this in your relative energy inequality in order to obtain your proper convergence. So you are able, through appropriate estimate, to have this kind of inequality in the end, where here there are several terms that they go to 0 when the viscosity and the Mach number, they go to 0. Then you apply here a Gromwald type argument again for fixed delta in order to have this kind of inequality. So if you assume that your initial data is going to 0, because you are in the same philosophy of the weak strong uniqueness, but now the Mach number goes to 0 and the viscosity goes to 0, you end up with this relationship. So before you send the viscosity and the Mach number to 0, then your modifying parameter that was a suitable choice for the initial data in order to have a smooth solution of the acoustic system and to use them in the ansatz. And then if you consider that indeed your smooth solution is of this type, you are able to show the convergence in this norm of the velocity of the Navier-Stokes equation indeed, or in this case, the kinetic energy of the Navier-Stokes equation to the one of Euler. So this term is going to zero because of this. And this term is going to zero because you can compute a suitable dispersive estimate that in the low Mach number limit, they will give you the possibility to lose indeed the contribution of the acoustics. I didn't mention here anything about the density, but from simple a priori estimate, you can prove that for epsilon that is going to zero, indeed the density is going to 1. So this means that in the end, this density here will go really to 1 and it will converge to the solution of your of incompressible order. So, and this was basically all the story. Here I just wanted to show you a picture that I found about the Bose-Einstein condensate. So if you imagine that they are boson particles and you have above some critical temperature Tc, when you go basically to zero in the sense of absolute temperature, this is exactly what happened. You will have a condensate, and your condensate can have indeed some oscillation that they are described by all the stuff that I tried to describe you before. So thank you for your attention.